Hi class, this is part 2 of section 6.2. Okay, and we're actually going to start right where we left off. So still example 1, and we're up to part E. So again, we want to label 3 points on the graph and any asymptotes. We're going to start with 1/3 to the x power. Okay, so this time our base is a fraction between 0 and 1. So we know we're going to get exponential decay. And then when I pick my x values, I can just do -1, 0, and 1. So this time I have 1/3 to the negative first power. So that would be 1 to the negative first power, but 1 to any power is 1. So I'm just going to write that as 1 in the numerator. The denominator is 3 to the negative first. To make the exponent positive, I'm going to move 3 to the first to the numerator. So we come up with 3. So when you plug in -1, we get 3 back. 1/3 to the 0 power is 1, and 1/3 to the first power is 1/3. So we're at -1, 3, 0, 1, and then 1, 1/3. Okay, so if you remember, this is actually the exact same graph that we ended with. Okay, so I'm going to put in the horizontal asymptote as well. Y is equal to 0. Since I didn't shift the graph up or down any, the horizontal asymptote stays where it is. Okay, so notice that the graph that we did in the last video, that was 3 to the negative x power, and that's equal to this graph. So 1/3 to the x power. These two are equivalent. Okay, so the reason why they're equivalent is if we start with 3 to the negative x power, I can write that as 1/3 to the x. So I'm bringing that 3 to the x to the denominator to make the exponent positive. But notice I just have a 1 in the numerator. So instead of writing it as 1/3 to the x, this is the same thing as 1/3 to the x power. Okay, so that's why these two graphs are identical. Okay, and now moving on to part F. So we have 1/3 to the x power. So again, exponential decay. We'll let x equal -1, 0, and 1. So 2 to the negative first power is going to be 2. Sorry, 1/2 to the negative first power. So 1 to any power is 1. In the denominator, you'd have 2 to the negative first. Bring it up to the numerator to make that exponent positive. 1/2 to the 0 power is 1, and 1/2 to the first power is 1/2. Okay, so we'll plot our points here on the graph and then sketch it in. So here is our exponential decay function. Okay, and then also the horizontal asymptote. So still the line y is equal to 0 because these graphs I'm not shifting up or down any. Okay, and part G, 5/8 to the x power. Let's just go ahead and sketch that. So we have 0, 1. If x is equal to 1, we get 5/8. So 5/8 is a little bit bigger than a half. And then when you plug in -1, we would have 5/8 to the negative first power. So that would be 5 to the negative first over 8 to the negative first. Switch them both, so 8/5. So 8/5 is a number bigger than 1, but not as big as 2. Okay, so we'll just put it right there in between and then sketch your graph. So here we have our exponential decay. Okay, so for this one, I didn't technically label 3 points. I only have 1 point, that 0, 1. My y-intercept is pretty good, but we could quickly label points over here. So when we plugged in -1, we got 8/5, 0, 1. Let me erase this. And then when we plugged in +1, we were at 5/8. Okay, for these functions, I'm looking more at the general picture. If you are asked to label 3 points, then please do so, so you don't lose any points for that. And also label the asymptote, so draw it in and then also tell me what it is. So in this case, y equals 0. Just like with the points, you can either label it right with the graph or off on this side. Either way is fine. Okay, so there it is on Desmos. Okay, so just to go over this one more time, properties of exponential function. If the base is greater than 1, we have exponential growth. There is no x-intercept, but the y-intercept is 0, 1. Domain is all real numbers. The range only positive real numbers, so that means 0 to infinity, parenthesis on the 0. We have a horizontal asymptote, and in this case, when we have exponential growth, it's a horizontal asymptote when x goes to negative infinity. So I'm looking here at the left side of my graph. As x gets really, really big and negative, that's when our graph has its horizontal asymptote. It's an increasing one-to-one function. Okay, if the base is greater than 1, okay, since it's one-to-one, it has an inverse, which we'll be talking about later. And these are 3 points that are always on the graph. So 0, 1, and then 1 comma b, negative 1, 1 over b. The graph is also smooth and continuous. So continuous, just think of that as being you could graph it without picking up your pencil. Smooth means it has no cusps or corners like the absolute value function has. And then if we have exponential decay, so if the base is a fraction between 0 and 1, we have this decreasing function now. Domain is still all real numbers. The range is still 0 to infinity, not including 0. Y-intercept stays the same. And these 3 points, notice they stay the same as well. When you plug in 1, you get b. Okay, but remember b this time is a fraction between 0 and 1. When you plug in negative 1, you get 1 over b. But if b is a fraction between 0 and 1, 1 over b turns out to be a number bigger than 1. Good. It's decreasing, like I said, exponential decay. And this time the horizontal asymptote is reached when x goes off to positive infinity. Okay, so complete these 2 graphs, enter them in through Canvas. So you'll graph first y equals 4 to the x minus 3, and then the second one is y equals 1/4 to the x plus 2. So in each graph, label 3 points and also the asymptote. Okay, I also want to talk a bit more about reflections. So reflecting about the y-axis that we've talked about, we had 3 to the x and then 3 to the negative x. So here in this picture, we have the graph of f of x is equal to 2 to the x, and then in red, that's reflected about the y-axis, and 2 to the negative x is the same thing as 1 over 2 to the x, which is the same thing as 1/2 to the x power. So it's exponential decay. If we start with f of x is equal to 2 to the x and want to reflect it about the x-axis, then we have the opposite of 2 to the x. So that negative is out front. It is not part of the base. Okay, so it is not negative 2 to the x power. Okay, this is actually not an exponential function because we have the restriction that the base must be a positive value. Okay, so this negative is out front. It's not with the 2. The base is still 2. So you raise 2 to the x power and then just take the opposite. So you get only negative values back. Example 3, the graph of f of x equals 2 to the x is reflected about the y-axis, stretched vertically by a factor of 3, and shifted up 1. What is the equation of the new function g of x? And then we also want to state the y-intercept, domain, and range. Okay, so we're going to start with our function 2 to the x. When we reflect it about the y-axis, it becomes 2 to the negative x power. Okay, so over here on the right, if I start with the graph of 2 to the x, reflect this about the y-axis, so we go from exponential growth to exponential decay once we reflect it, and this is 2 to the negative x power. Okay, now it's stretched vertically by a factor of 3. So we haven't talked about that in this video, but we've definitely done vertical stretches before. So remember, vertical changes are just what you think. So if we're stretching it by a factor of 3, we're going to multiply this by 3. Then it is shifted up 1, so plus 1 at the end. Okay, so this is the equation of our new function g of x. We now want to state the y-intercept. So anytime we want the y-intercept, we let x equal 0. So g of 0 is going to be 3 times 2 to the 0 power plus 1. Be careful with order of operations. So we apply exponents before we multiply. So 2 to the 0 power is 1, and then we multiply 3 times 1 to get 3 plus 1 is 4. So the y-intercept is 0, 4. Okay, and next the domain and range. Okay, so looking at the graph here in blue where I reflected it about the y-axis, if I now stretch it vertically, 0, 1. So stretching it vertically means, so we're going to multiply all the y values by 3. So we were at 1, but we multiply by 3. So then the y-intercept would be here at 3. Okay, we still have to shift it up 1, so that's why it eventually switches to 4. But if we just reflect it and vertically stretch it, we'd be up at 3. And then you would still have the same horizontal asymptote. Okay, because we're just stretching it. So far I haven't shifted it up yet. Okay, so I'll stick with blue. So here where it was increasing, that's been stretched, so it's increasing faster. And then here, all of those y values were multiplied by 3 as well. So this is what the graph would basically look like if you vertically stretched it by 3. And now move it up 1 unit, and that's what's going to change the horizontal asymptote. Okay, so if we take this graph and shift it up 1 unit, then we get 0, 4 as our intercept. And then this new horizontal asymptote here at the green line, which is y equals 1. Okay, so even without graphing it, hopefully you see that having this plus 1 here at the end, so shifting it up 1 is going to shift that horizontal asymptote up 1. Okay, the domain on all of these functions is all real numbers. So that is still the domain even after these transformations. And the range is what has changed. So the range was 0 to infinity, but then shifting it up 1 switches it now 1 to infinity. Sketching it was extra. You didn't have to do that. We found the y-intercept pretty easily without the graph. Okay, the domain for exponential functions is always all real numbers. The range starts off 0 to infinity, but then if you shift it up or down, the range will change accordingly. Okay, so here's one for you to try. So example 4, the graph of the function f of x equals 4 to the x is reflected about the x-axis and then shifted down 3 units. What is the equation of the new function g of x? State the y-intercept, domain, and range. Good luck. Let me know if you have any questions.